Greetings. So today we will talk about lists and tuples in Python. So those are some of the most common, if not the most common data structures in Python, besides dictionaries and the lesser used sets. So these are the first compound or complex data structures, meaning that we store multiple items. Previously, we talked about strings, which you can think of them as sequences, also of single, small, tiny strings, single character strings. However, list and tuples offer us a more flexible way of storing, well, pretty much anything, meaning we will be storing our primitive data types. So we'll talk about all of some difference, what we can do and what we cannot do with some of these data structures, and also the typical use. So let's start with a list. So this definition is a list is ordered, meaning there's specific order. Doesn't mean sorted, just ordered, right? Mutable. This is also very crucial. This is the first mutable structure we encounter, meaning we can change individual items. Unlike, remember, we could not change strings directly. Strings are immutable. You have to make new strings. But lists you can modify. Also, we can change the size. So it can change the size to be smaller or bigger. So two different things. Mutable being individual members, size being more items or less items. So typical syntax, we'll talk about this. Again, square brackets, again, very common. On can have duplicates, can be nested, meaning you have a list of two-dimensional lists or three-dimensional and so on, right? On the good news for you is since you already learned about slicing and indexing for strings, we can use it also here for lists. So again, let's start with why we actually need this type of structure. Again, small tiny principle example. We have some items for grocery shopping and we would have to make new variables. 1, 2, 3. Is this a good way to do it? Well, for 2 items, maybe you can still survive. For 3, okay. But you have 15 items. You have to make 15 variables. Not a good way of working and certainly not something you want to do for 100. So again, philosophically speaking, these lists are for storing something homogeneous, meaning similar items. Yes, in Python, lists actually are very flexible. You can store pretty much anything, but the core idea is we have something similar, some similarity, very wide definition of similarity or relatedness, basically, and we want to store them in a single variable. Again, I have already opened the Google Colab, right? So again, you can open this yourself. Again, the link is here. Will be provided on the in the course materials on. So if I run this, obviously, right, it will work, right? And of course, it's run by me, not by Google, right? Run anyways. All right, yeah. So all right. So the better way to do it is this way. So we provide a list. And again, those who have taken some other languages, such as JavaScript or I don't know, C or some other languages, will see that these lists in Python are closely related to arrays in many other languages. They call them arrays, sometimes called sequence, maybe less often. That's a more generic term, actually. But so don't be if those who have taken any if you had taken any computer science classes, linked lists are not the same as lists in Python actually. So that would be something to not the same thing. So lists are very generic in Python, very generic. So and again you see here if I run it, right? Bread and milks, right? I could also we'll see we can also add some more things. So already here you can try play around. Maybe again so these are three strings. These are three separate strings, but we store them as in a one variable. Hopefully you see that this is actually quite nice, right? Again, this is basically a big step in general growth of you as a coder, as a programmer, in fact, as a researcher, right? Of course, you want to store similar things in some sort of structure, right? So let's go through all the basic things we can do. So we can find length, which is fine. Length of the empty list is 0. How about our groceries? Well, 1, 2, 3. We expect to see 3. Will we see 3? Indeed, we should see 3. Right. So notice again, so sequence, again, list is type of sequence, and sequence offer you a length function. So strings have length, and now lists have length. So length is a function, takes sequence, and returns this number. So crucial thing, remember in our string, we could check for substring. Similarly, but not quite the same, we can check for exact item in our list. So is there bread in our groceries? What do you think? It should be true. So how about bread in empty list? It should be false. Still false? Yeah, indeed it is false. So my breadsticks, right? So bread in food. So here's the thing. So uh, if we check here, my breadsticks, right? There is bread in breadsticks, right? That's for strings. However, notice important point. If I check for bread with some white space, right? This is going to be false because lists do not give you sort of fuzzy search by itself. Yes, you can do it, but you have to look inside individual items. So you cannot search directly for something which is approximate match, right? So for for searching lists, we look, we need we need exact item, not something fuzzy, right? So not something fuzzy, right? So again, you run it. I already run it. So true or false. So again, so bread and groceries again, it has to be exact match. Again, why was it false? Because this was lowercase. And apples obviously is also not present right now. So yeah, we can do some things here. We can make a list out of strings. Well, what do you think is going to happen? Well, it's gonna make us a just a list of individual characters, right? So these are basically six tiny strings and they are in a list. So this could be, so I could do this, my breadsticks, right? I could convert them directly, right? Convert on the fly, right? So notice you cannot, not everything can be converted, right? So not everything can be converted string, no list, not everything can be converted to a list, right? Primitives cannot, right? Because, well, let's see. So let's try it, right? So we will see lists, right? Number five. Five is just a single number, right? Or even 5,000, doesn't matter, right? It doesn't matter. It's still a single number, right? You think, okay, maybe that's five, 1, 2, 3, 4, 5. No, this is not going to work. However, right. So we could do this. We could convert. We could make a string, and this would work, right? So this would actually work, right? Because why? It's a tiny. We would get right. We would get. We get. We get a list of a single string, right? So let's say again, I'll do something like 5, 1, 2, 3, right? So you see, it's not. It's gonna now. It's gonna be what 1, 2, 3, 4 strings, right? Yeah. So let's see here, right? 5, 1, 2, 3, right? Why? Because this was not breakable, but once we convert to string, obviously we could break it down, right? So once it's string, once it is a string, we can break it down into a list, right? But not from a number, right? So again, important point. Now, so single item list, we saw this, right? This is comes as you want to start with just not an empty list, but have one item. That's completely fine. Again, you can do it again, list V, also be single item. So name list here, right? And we have some lists. So list indexing is just like string indexing as far as access goes, right? So indexing, let me finish this, let me clear this up. Yeah. All right, so indexing. So individual. So again, Python, right? 0, 1, 2, 3, 4 minus 1, 2, 3, 4, right? So individual letters, very similar to string indexing, basically the same thing. So my name is Valdis, right? VALD, right? So this is a fourth letter, right? So fourth character, right? So how about our groceries? Let's remind the groceries. So let me get my second. So this is eggs, right? So here eggs. Could be second. Right? Index one, right? Indeed, we got eggs. Let me show you again, right? This is X because second, right? So very similar idea. So again, name list, right? I could do this, man. So ID, right? I could do second from the end. I can get this one. Also get this one here as well. Same thing works. But now we come to the difference. Now, unlike strings, we can change, mutate. CS terms, right? Values in string. Content of a list, right? Sounds kind of scary, mutation, right? So I can do instead of I can change it, right? I can change whatever I want. And now my fourth item with index 3, right, is D. So the only thing now is okay, you think, okay, that's great. Now I would like to have this string together. Well, there you might come into some unexpected snag. You think, okay, I'll convert the list back to a string. Will this give us what I want? Not quite. So this gives us a literal string of how list would look, right? So we got this. So this is extremely rare to the one. So do probably, I don't know whether it would be very practical. So what you would do is again, so the same thing again, right? This is what I did. So not quite what we want, right? We got this strange string which has brackets, it has quotes inside, but this is basically a big string, right? And that's not very. What if you want just individual letters? I want to evolve this back just with a capital D, right? Well, so you use join. So, and this is a string method. This is not from list, but this creates this one. Sorry, so this takes any type of sequence and joins it with something, right? So the only crucial part is this part here should be only strings, right? It should be joinable as strings. If you had something, one of these was number, like the number 5, or 5,000, just not a string 5,000, but just a number, or maybe true or false or something else, it will not quite work. So this part here, join, very crucial, right? In text manipulation, while this, right? So you can use any string, by the way, right? You can use smileys, you can do this, right? So this is provide what's going to be joined, and it's inserted between each member of the list, right? So play around. You can play whatever you want, put smileys, whatever, emojis, or other letters, right? And maybe I have some other, yeah, something like this. Yeah, funny name. You can put some cowboy hats, right? And indeed, you get all this, right? So grocery string. So this also works, by the way. Why does this work? Because individual groceries are strings. If they were numbers or something else, it would not work. So similarly, now we come to the second part is we can go the other way. We can split the string into a list of strings. So that's kind of candy if you're doing some text analysis. So split. We start with the sentence, right? This is string, right? And we use by default, split is quite nice, already default. We take a string, so this is a string, the variable is calling string. We split by any amount of white space. So let's see, we will get words. So all this is teaching Python, right? At RTU, right? RTU, right? So these are all, I can have some extra white space here. And we have 1, 2, 3, 4, 5. We want to call these tokens, right? These are words. In this case, we can call them also tokens, right? Units, right? So we split. So we did lose something, right? We lost the white space because we don't, again, by split here, it is a sort of say very flexible. It takes any amount of white space, right? So you have extra spaces, those are gone at the moment, right? So you can't really get them back at the moment like this. So while this is flying Python, right? Sure, why not? So I change this third word, right? I can mutate the third word to flying. While this is flying Python at, by the way, let me change it again at. This is Latvian R at. Sorry, let's do it again. At. And so, of course, this is now correct at. Right. So now we can change back. Now, and of course, how we learn this trick of joining. So I'll use single space again. Notice again. So this we will lose extra white space, right? Here. Well, this is flying Python at RTU, right? So this method of deconstruction of strings in the list and back, right? Very useful when we need to modify some individual items in the longer strings, or in general text analysis, very common. Again, split, you can split by other things, yeah. And also, I should mention, yeah, split can be used. You can split by pretty much any character, such as comma or anything else as needed, right? So it doesn't have to be only split by white space, right? And we can also use regular expressions for split too, right? So let's go back to our more list operations, right? And now talking about strings. So range to list. So range, remember I told you, range is a factory. So it gives you numbers on demand, and sometimes you really want those numbers on hand. So we can do this. So this is a sort of factory, lazy factory, right? It only gives you numbers when you want them, like in a loop. But if I want a list, right? In modern Python 3, we use list, we convert it basically. We say we force it into a list basically, and we actually have the numbers, right? This is a quick and dirty way of making, pretty much any number of integers, right? You say start. Notice, of course, in this case, I did not. 120 is not included because that's how range works. The last number is excluded, and of course, step. You can just play around, see what you get. So we come to the next part, slicing, the next best thing since sliced bread. Uh, Slicing lists work just like slicing strings. So first three numbers would be 0, 10, 20, right? Last three numbers would be implied, right? 90, 10, right? Makes sense, right? Again, this is comes in implied, and this also is implied here. So middle print number, so fifth, so this will be sixth number and sixth and seventh number, right? Eighth number is not included, so let's count it. So six and seven, so 1, 2, 3, 4, 5, 6, right? Matches, and seventh also matches, and eight, right? Index 8 is not included. So, all right, index 7, sorry, not included. So, and again, we can reverse. This is also fun, right? We can reverse the numbers using the same approach we use for strings. We basically simply go back, right? Using this -1 syntax, which is not quite the way would it work if you followed exactly the logic, but it's such a handy shortcut that has been in Python, has been using it for a long time. So again, if you want every second item in a list, sure, every third and so on. Maybe you start with the second number, sure, why not? And again, skipping. So again, this part here means we go to the end. If you want to stop earlier, you'd insert the index where you want to stop, right? So like in here, in this example, we started what fourth number, which is 30, right? We go to the 10th number, but it will not be included, right? Right. So, okay, so as long as you have, now we come to some cool things for some operations we can do on lists, which are not for every list. If it's not a string, strings you cannot add together, but as using, I mean, you can add for some, use join, right? But here we can use sum for numbers. Also floats, right? So we can sum all the numbers around, right? So if you try summing groceries, it will tell you some groceries in string. And here you might be asking, where did this integer come from, right? Because if you think, okay, we know Python offers you over plus as an overload operator for strings. Those were really smart of you, right? That you are. So you might think, how come sum doesn't work? Well, sum has sort of starting value. If you check here, maybe Google's not cooperating with me. Yeah, there's a start value, which is by default integer 0. So that's where this integer comes from. So that's why it doesn't work. Because there is, you have to start with something, right? You cannot start with nothing, right? So by implication, right, you can actually supply this start. So that's why sum does not work with strings. It only works with numerics. Again, but nice to have. So print save number slice, right? We can sum that, right? 30, 50, 70, right? That sums, right? So now we can use print and f strings to save any to not save any results. So for example, again, reminder with f strings, I can do whatever I want here, right? So I can print the list. Again, f strings pretty much formatted strings will print you. This is a whole list, right? And it will sum every second summer num. So this is basically every second number, right? So that would be what 10, 30, 50, 70, 90, 110. You have to trust me, but you can try it yourself. This is 300. So now you may say, okay, how about average? Well, there is average not defined in standard, in by standard in default. It is in math, in statistics, of course, statistics module. Yeah, but you can easily do it yourself, right? So, as you all know, Mean, right? Mean is, yeah, like I said here, statistics module. Yeah, so average some numbers divided by length of numbers, which is of course 55, right? Why 55? Because 0 on 110 is 55, 10 on 100 is 110 divided by 255, so on and so on and so on. Yeah, easily it is. So again, it also will work with string, but the min and max does work with strings, by the way, but it has to be comparable. So yeah, min max also works, min and max also nice. So again, lists are compound. So now we come to a sort of, so let's take those who have been following or new to this, maybe take a little break or just rewind this, and we come to the next important concept, copying and how memory is used in Python, and actually that applies to other languages. But since lists are compound structures, they're built from other elements. So by default, this is one of the sort of does not list does not copy automatically. So here I'll show you. So look at this here. If I make a list out of groceries, right? This is a copy, right? This is a copy. What are these IDs? You might say, okay, this is what's called virtual memory addresses, and we don't really care about what they actually mean. What we do care is that they are different, right? So they're different places in memory. I created a list. However, so this is where the mistake comes. Not mistake. Oftentimes you want, but this is just an alias. So this is just an alias. So this is part here, I'll show you, right? So the copy has its own memory address, right? We made a copy here, right? That's a copy, right? This is copy. However, these first two, glist and groceries, right, actually have same address. And so what does this mean? This means that basically these are shortcuts. Groceries and glist2 are shortcuts to the same list. We call them reference, we will call them pointers, right? Similar concepts, but not quite the same. So groceries too. So if I change, so this means if I change something, this will modify what? To modify, of course, obviously the other shortcut also is looking. So originals modified, the copy, this one here, the other, the list copy, right, is not going to be modified. So very crucial point, right? I should probably call this glist. I should probably call this glist alias. Glist alias would be a better name, so it's easier to see. Glist alias. Yeah, let's see this again. And it's not going to change anything. This should be the same memory, right? I have three actually. I still have the GLS2, right? But I'm not going to use it now for next lecture, right? So this would be a better name. I just thought this GLS2 is not maybe right. So this is an alias again. So what? Let's take a look at our so bread, eggs, chocolate, right? So groceries, chocolate. My third item is chocolate. Second alias, also obviously a shortcut, the same idea, same data, also same same contents, but the copy is not modified. So why am I talking about this so much right now? Because this will come up again and again when you work with Python. It's a common source sometimes of errors when working with complicated structures. So most of these complex structures are not copied explicitly. You have to tell Python to copy explicitly, right? There's also a copy command. So if I change beer, well, I'll change alias, right? Let me add some beer. Glist alias, right? And glist alias, right? You can change groceries. So suddenly we'll have to buy beer. Like that idea? Hopefully you do, right? So same thing groceries now instead of eggs. Beer, beer, bread, beer, chocolate, right? That's groceries. And I changed by because I used L as an alias. I mean, I have 50 aliases for same ID, same data. So why is this approach used by default? Because you have millions of items you're working with. You don't really want to copy unless you really need to, right? So list copy again. So it's possible. We eliminate copy. So potatoes, right? And now again, list alias, glist alias, right? I'll make right? Potatoes, if I had potatoes here instead of bread, of course, I will have potatoes here, but now my lists are completely different, right? Two completely different shopping lists. So again, so this is not content, right? And this is, so there's a new check, is actually checks whether this is the same, right? So this check is for checking whether you have ID, whether this checks the actual memory or if they are actually alias. And if it's true, that means yes, they are same data. Now, again, so I make completely this, like, so if I make this, right, potatoes, egg, milk, potatoes, and milk. So, again, so this is just a new list, right? But, so, notice here, list 3 is actually same contents, potatoes, egg, milk, right? Eggs, milk, right? Exactly same contents, but they are in fact two different shopping carts. You can think of them two neighbors or maybe very complete strangers, but they just happen to have potatoes, eggs, and milk in their shopping carts. They are completely different as far as memory goes. They are completely different place. Okay, so I mentioned already this copying. So this is actually, maybe I use list, right? So another copy. This is probably the common way of doing it, right? So this is actually, I would avoid this one. It's a little bit hacky. It is actually, you make a slice of everything, right? And that also makes a copy. But this is what you would probably do. This is the most clear. It says, okay, I'm making a copy of list 3. Yeah. So you can check here. These are actually going to have the same memory address. So potatoes, egg, milk, right? So let's see, potatoes, egg, milk, right? These are copies. Notice. So same contents, but ID in each case is different, right? So different memory addresses, right? So, all right, go back to copy, right? And I'm gonna be, I did this before, so I'm skipping this already. So if we come to the next part, now I already mentioned that lists in the very beginning, the lists are dynamic by their very definition, right? Let's see if I'm recording this. Would be a shame if I was not recording it, but I am recording. Very good. Okay, so unlike strings, we can add more stuff, right? We have a shopping list, right? So we cannot add arbitrary place. You know, put apples in 501 item 501, right? No, that's not gonna work. List alias or maybe groceries. Let's do groceries. Groceries. Yeah, bread, beer, chocolate. We cannot do it. I'll make it groceries. Yeah, groceries. I can't. I sound like French. Groceries. Right. So in place modifications. So again, glist. I guess I'll keep this the different variable. So let's create a new list. Apples, bananas, oranges. Right. So we come to the next again. Maybe take a little stop to reabsorb everything because we come to the next concept, which is again gonna come up again and again in your future if you are not coming up with this. So in place versus out of place. So what does it mean in place? We have a data, right? Data structure, a list on this. Look at this syntax here. G list append peaches. So this is going to be the first time, at least in this course, where we encounter adding something to existing in place. Meaning, what does this mean? This means that this part here, this data structure is going to be modified. Because why? Notice I don't have a equal sign anywhere, right? So append, and I'll show you right now, apples, bananas, oranges, peaches. And I'm also careful with careful note about in notebook, right? If I run this cell multiple times, I will add more peaches, right? So let's do that. Let's do a couple more times. So I'll do one more. It's peaches again. You see, I'm modifying glist. Right? And I can do peaches forever if my finger gets stuck on the run button. So autoplay. So compare it again. Autoplay is what I've been working before. Strings, numbers, right? All autoplay. So this is actually going to be a new list. So if I add pomegranates right to my big list, right, I will have apples, bananas, orange, peaches, pomegranates. So notice, compare. See, new list, pomegranates, granates. I can't spell it. I guess old one, original does not, right? So that's a big difference because I'm basically affecting. So sometimes when you are busy with lots of analysis work, right, you might forget which one did I modify the original or not, right? So you will see there are many methods for different structures, which usually they will tell you is this in place or out of place, right? So in fact, generally, if you're not if it's not returning anything, right? Well, then it's not, you are modifying in place. So list copy right here as well, right? That was like X list right here. All right. So now cutting down the list. Remember, if you need a shorter list, you can cut off the G list, right? Or here before slice, we had apple, bananas, orange, peaches, right? Remember, pomegranates we didn't add because we did not modify it. So we can cut it. Basically, this is a very simple approach, very common. Remember our friendly slicing syntax. We can simply add it and use it, and we basically override. So this is out of place because this creates a new list actually, right? Slicing does create a new list, right? And some language doesn't, but in this particular and some structures, but for lists you do create a new actual structure, right? So this is basically I'm making copy, but smaller copy, not a full copy, just a partial copy, right? And assigning the same variable. So of course, original would be gone if we do not have any other reference to it. So it is also notice this interesting thing is if you only have a couple items left, would this be an error? No, because remember, slicing syntax does not provide any, will not give you errors if you make a mistake in your indexing. Like if you have, you want to say 4,000, it will give you everything, right? So it doesn't matter. So now, of course, I can keep doing this over and over, right? I can put 4,000 right here, right? It doesn't matter, right? It's not an error, right? Obviously, if I did um, something like two, I would cut down to only two items. But now I have four guaranteed, right? So, okay, so my list copy. Do I still have list copy? I forgot that I have. Oh, has three items, right? On yeah, again. So it's still going to be three items basically, right? In this case, five, but actually three items, right? So groceries. What does my have here? Yeah, I only cut down. Okay, so we come to another thing is that if you end up creating lots of different copies, and sometimes you are overwriting things, Python will manage memory for you. And if you have no reference to a particular list, just or any other data, your memory will be cleaned up automatically. So this is something you don't usually pay attention. It's very nice to have. It's what most modern languages have. The so-called garbage collection. The big exceptions are of course the so-called system languages such as Rust or maybe C++ and C, where you have to do it yourself, right? So this means that generally you don't have to worry about the memory usage explicitly, right? So uh, so you don't have to worry about memory leaks directly. So that's a nice thing to have. Okay, so comparison, right? Clear list, right? Maybe you have something else, but yeah, this is all stuff we did before. Let's uh, now come to, let's see how well we're doing. We have about 20 more minutes to do it. So list methods, yeah. So list methods, very good. And so we saw append, we only saw one method, which is append, right? That's a method in place. There are many more methods. You can look up here, more lists, right? We can use a directory, which is the old way of doing it. You can still do it. It shows you all the different things you can do, but you got to look at all these are so-called the internal ones. You don't worry about those right now. These are the ones you can do. Append we saw. So if I do this glist dot, right? You see, I get all of these. Append, clear, copy, right? So good IDE, Visual Studio Code, or even Google Colab, assuming it's not asleep, right? It will give you this access, these methods. You don't have to remember them, right? Because again, if you work across multiple technologies, languages, you might not forget, okay, was it append or add, or was it count, or I don't know, length or something, right? So glist, right? We have our glist still. I don't know what I have here. Oh, it's empty actually, right? So I have clear actually, right? Let's start with that one, right? So, yeah. So I have clear, yeah. So here on, right? Actually, it was empty, right? Maybe I could show you here, glist, and let me add something here, so you can see this equals something, maybe something apple banana, right? And I'm sure you trust me on this, but still, banana, right? Doesn't matter, but still, right? So apple banana, and now it's clear in place. Careful. So this means you have an empty list. So I'm gonna append T on the append. So append unclear, right? Append by one at the end. right? So there is something else. There is extend. And again, maybe less used. So extend is to make a flat addition. So notice here, I'm gonna milk cookies chocolate to my tea, right? My afternoon tea, which I still have a long way to go. Tea, milk, cookies, chocolate, right? So it's different from append. Look at this here, right? So notice the difference. But here I create actually a nested list. It's most likely that you don't want. Maybe sometimes you do. But here, so this beer cognac, right, is actually a new list, right? Inside the list, right? It's an item. Yeah. So we probably don't know. So how do we get this beer out? Right. So let's look at our last item. Yeah. But maybe you want to access nested list. This is a good time to check our nested list access. So G list. Beer cognac. Nice. So, so this accesses the last item, right? So if you need the beer out of it, you will get glist minus 1, 0. You can mix and match different indexing methods, negative or positive, right? So this is how you access two-dimensional data, in this case, beer. So there are other ways, right? 4, 0, right? Because fifth item, 1, 2, 3, 4, 5, right? And also 4 minus 2 would work also, beer, because this is y minus 2. That's kind of silly, but this means minus 1, minus 2, right? So, okay, so that is how we access. Now we come to pop. So pop is something that destroys in place. So pop destroys, well, it removes, it returns the last item. So you can assign it. If you do not assign it, we would lose it. So it's use it or lose it. But the more it modifies again in place, very important. So if I do it, and I'm only going to do it once. If I do it again, it's going to. So originally I had beer and cognac in my for my afternoon tea set, which is not appropriate, right? So I got my original back, and I have the last item separately. It's not part of the original anymore, right? So I'm not going to do it again, but my chocolate will be. So if I do it again, it'll be chocolate gone, cookies, milk, and tea, and so on, right? So let me print my list, right? So notice G list, and my chocolate is gone forever. Why? Because I didn't save it. So pop by itself destroys the item, I mean returns the item, but if you're not using it or not saving it or doing something with it, you're not gonna have the last item. All right. So let's do okay, let's make a list and of course back to 4. All right. So there are a few more helpful methods. I'll kind of slowly go over them, right? So reverse is just changes basically in place. So reverse, what's gonna happen if I do it again? It is also gonna do it again, back and forth, try it again yourself. So in place, it modifies the G list. How about out of place? So notice, compare this reverse to what the method we already know, minus 1. This creates a new list. So there's a big difference. So if I do this, I have chocolate, cookies, milk, bread. This is completely different now from the original list. Now they have two different places in memory and live somewhere else, right? So yeah. And of course you can play around with this, right? And see how it reverses, right? And so on, so on, and so on. Right. So now let's go to some numbers. I think we do some. I think we already did this already. List numbers. Yeah. Uh, we already did some calculations. I already showed you this already before. For example, here this is the same thing we did like maybe 20 minutes ago. So, but lists can take any number of data types. I mentioned this. So yes, you can do, you put whatever, right? So I put some numbers, I put some strings, I put another lists, couple of lists here, actually list within lists, right? So really messy. So this is actually three-dimensional here. That there's a list with a list with a list. And this is just another list, right? So, but yeah, and you can adjust it, right? For example, right? So let's go to our numbers list, in place, out of place sorting. Sometimes you want, if you can compare things, you can sort things. All right, so numbers list, you can sort it. So what does this do? This sorts the numbers list in ascending order and modifies it. So notice this 888, right? It is nicely sorted now, 888. Okay, if I append, it's at 12. So now it's not sorted anymore. It should be here somewhere, right? So numbers list reverse, we can do that again in place, again in place, meaning this list is being modified. Remember. So compare this now. So this is the reverse list, right? It's nicely sorted. So sorted, there's another way of sorting things, auto place. Many operations in Python have this sort of duality, right? Hegelian sort of duality that you can sort things in place and auto place operations, yin and yang. So we can do it also auto place, right? So this is completely different list from this. No relation whatsoever anymore. And so memory, right? You can add things, destroy it, whatever you want. It's not related to the numbers list anymore. Right? So we can sort letters, by the way, because letters can be compared alphabetically, VADILS, right? That's ASCII values, right? So if we sort Latvian letters, right, we will have a right. Q is last because that's a Latvian letter. After and space is first. That's something to notice, right? So counted index, right? So we can count things. Number 12, right? Let me show you the list. Print the list. So we probably forgotten what it looks like. Print sorted list. Yeah. Yeah. So I'm looking for number 12. Count 12. Yeah, count 12. Right. Ah, yeah. And a numbers list count. That's one. Yeah, one in each list. Okay. Maybe let me add one more. Maybe append pre sorted list append 12 n. Right. I got. It's not no numbers list. Numbers list because it's not sorted. Yeah. Append. I don't think it's sorted, right? On the print numbers list. Let's see what we have. I forgot already. Maybe I forgot. Oh, my Google is now asleep. Maybe we'll have to stop. Oh, oh yeah, okay. So yeah, we saw what I want to show you, of course, is that this original one has 112, and here has 212, and those are counted, right? So I could count letters, cut letters, count three. We have three eyes, right? You can count three eyes in this here because one, two, three, right? We can count them, right? All right. So we can find index, right, of number 12. So index, you don't have find. By the way, we don't have find. Remember, string used to have extra method called find, and list only have index, which gives you index error if you don't have the value. All right. So to finish this, we're getting close to the end. So insertion, you can insert specific way. So one thing I should mention, this is generally not recommended. Insertion is heavier. So if you have a huge list, you can insert arbitrary things and arbitrary spaces. So what does this mean? Is at the place 2. So this is 0, 1, right? So index 1 is bool. Everything else, all of this gets shifted, right? So shifting in beginning, that's very inefficient operation as far as memory goes. Yes, there's some ways we can do to alleviate this, but in general, this is not recommended, right? Unless you really need to, right? So remove bool, right? Okay. So let's try. We have sorted list. Remove bool, right? Let's try it. Yeah. So we have sorted list. Okay. So now, if I do it again, I'm not going to do it, but I can show you, right? I have sorted list. If I do this again, I don't have the bool anymore. It will throw an error. There will be an error, right? So you can try to show it to you if you want, right? There's going to be an error, right? We see. Let's remove X is not in a list. Meaning, what's X? X is bool, right? So now my big question: how do you remove multiple items? One way of doing it might not be efficient, on large lists, right? So, my way to do it, you have a needle, whatever you want to remove, and while needle is inside a list, you remove it. Not the best way, maybe do it, but you can do it. So we have 12, right, and it is gone, right? Speaking of that, right, this is while needles inside a list, we come to the looping. And that's good news for you is that you can simply go through the list and loop through it because it's a collection. So my G list, simple. Same syntax we use for range, we use for strings, or item in G list, right? So this is a new variable. taken, create a new variable, we create a new variable. So item is just a variable name we came up with, right? So notice again some other language like in JavaScript used also like you have indexing, right? You don't use index. So sometimes, but it's very rare in Python at least, you need an index. So you use this approach. You enumerate the items. So then you have two variables. And I call it index and item. You can call it X and Y or I and C or whatever. But index item is, I think, pretty descriptive here. So I can print. I have my original. So index item, so index item 0 is bread, same as bread, right? So again, we could use this, right? If you really need to. I mean, bread is same as bread. Why? Because item, right, is same as accessing this by index. But again, this same in this part usually you don't need it because you already have the item, right? I'm just showing it. It is indeed the same. Now numbers, right? So let's do some typical workflows. You have something to work with, right? You need to do some modifications. So what you do is this. You start with something empty. Let's say you want to have squares of these numbers. So you have empty. So this is very typical, sort of like a template, or in Latvian we call this shablons, right? So you start with something you want to work with. You have something you are going to be accessing is. So numbers are what we're going to work with, right? So we go through every item and we create a new square value, right? We do something with this item, right? In like sort of generically speaking, and we square it and we append to the results. In this case, we call it squares. So I recommend you do this, you should go through this slowly, right? Squaring, 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 and I have my squares. Pretty nice. This part, next part, is actually a little bit more intermediate or advanced. I was not advanced, but intermediate. What I did is so common, right? This approach, right? So if you knew this, maybe first, this is your workhorse in general, right? We have a new list, and we want to do something with older values. We want to go over other values. So you can do the same thing we did in a short syntax. So basically, this is a very compact way of writing. So we have some sequence. In this case, it's a list. And we make it, n is basically a variable we create, and we assign the new value. Right. So this is for sure. So this is not something, once you get used to it, once you get more experience, I use this a lot, but in the beginning, maybe it's not as clear as this original example for looping. So start with this. It's speed-wise, there's almost no difference, right? But once you get used to this, it's very powerful. So, because also it's powerful because you do things like this also. You can write in one line, like 4 lines of standard logic. So n squared for n only if it divides by 3. So only those who divide by 3 without reminders. So I call this even squares, so this. But again, if you seems like kind of strange, it's exactly the same as I did here. So this would be the classical way of writing, like I did for 30, 40 years, right? You have a start is blank list. They're not technically even squares. They actually divide by 3 squares, right? Oh no. So if n divided by sorry, you see I have to fix it, right? 3, right? So uh, thirdly squares, not odd, but yeah. So there's nothing left basically, right? So even squares, right? In numbers, right? I don't know what my numbers were, right? N divided by 3 is never going to be 3, right? It's going to be 0, right? Yeah, exactly. Not 2. Yeah. So, right. So again, even squares would be actually this, right? 2, right? This would be really even squares, to be honest, right? Right? Because 0, 10, 20, but what do we have here? Numbers, I forget what the numbers are, print numbers. Yeah. Divided by 2. In this case, of course, everything divides by 10 divided by, so divided by 4, maybe 4. Yeah, let's divide by 4. Yeah, 4, right? Because 10 this doesn't divide by 4, 20 does, 40 does, 60 does, 80 does, 70 doesn't. Okay, yeah. All right. So in a list, right? Yeah, in a list, we already saw there's accesses, right? So that's not really that important right now, right? You can access, right? List. Now we can use this access, right? But we don't need to look at it right now. Append, these are already covered. All these methods are covered. So what do we have here? Sorting, all this we've done already. So with this I'll remove this from the materials because we only all did this in a complex sorting. Let me see if we have anything else left. We saw list comprehensions. So we are actually laying some in. We did everything, right? So do we have anything else left? Oh yeah, this might be a little bit. You can do this. I'll make a link, a small. I think my recording is slowing down. Text. Mm, yeah. So, then yeah. So this is sort of shortcut. So you have a small. You start with a tiny list, right? With just one item, and you multiply 10 times, and you have basically 10, 10 size items. It's just a convenience, and you can say, okay, my counters, right? There's the one here, right? Sixth item, right? And you can play around with this, and you have your list is increasing here, right? All right. What else? We only check existence check. We only did all of this removal, right? And yes, my sorting. We already did everything. All of this. Now, oh yeah. And again, this is just a review. Just a review, I think. Oh yeah. Yeah. So these are all the methods: append, insert, extend, index, remove, sort, reverse, and pop. So most of these already. Again, most of these are in place. Which one is not in place? Well, index of course just gives you the item. It doesn't affect anything because doesn't mean all of in place. But extend, insert, append, remove, sort, reverse, and pop. These all modify the list. Right. So that's very good. And I think we are actually have covered this. So, oh yeah, we come to the tuples, and you might be saying, okay, what about tuples, right? In fact, right? Yeah. Before we go to that, there's a question. What if you have a list of different breads, right? And you want to, and we also have milk and eggs, but you only want breads, right? So, and we saw this in the very beginning, right? We want only bread. So this is approach. You have an empty list, again, a loop, found list, what we find, we don't have anything. We have a needle. Well, in this case, luckily it's bread, not needle. And we check inside the item itself. So for item in growth, if needle in item, right? If bread is in our text, then we found the list append and we find all the new list, right? So we didn't get chocolate bread. Why? Because we had sensitivity. So if you want to modify this, uh, what we do is we lowercase both of them, right? We check the lowercase version or uppercase version, right? So now we have also a chocolate bread with lowercase, right? Because we checked the small version so it will match. We normalize them basically. Okay, so that was helpful. Yeah, on tuples, to finish this, there's nothing really interesting about tuples as far as they are basically immutable lists, meaning you cannot change tuple size, right? So you can assign them using commas. And if you see this part here, comma, right? I don't have to even use parentheses, right? So 3, 6, and so this is fixed size. Philosophically speaking, right? So my big question, why do we not have tuples? Well, they're slightly more efficient because they're fixed size, right? And they only have two methods, right? But the idea is this: tuples are for heterogeneous data, meaning different types. So, throw anything. And lists are for similar type. It's just a guideline. You can mix and match either, right? So tuples are more efficient, right? So you can create tuples using tuple, right? You can do all the things we do with lists. So again, I'm not going to spend much time. One thing you might want to look at is tup unpacking. So you have two values, A and B, just singles. And again, since it's comma makes tuple, so we have a mini tuple, two items, right? So number tuples, right? 8, 9, 10, right? Slicing works, right? I can also go the other way. I have a tuple, right? 5, 9, and go the other way. Of course, I have to know what the size is. There's also without size, right? So what this means is this packing leads to this little trick. You have two values. In my language, you need a temporary value to swap values. Here, we can use this little trick. It says 5, 9, now it's 9, 5, right? So very handy. but again, not strictly necessary, right? And for those who want a deeper dive into this, so to say, since we're running out of time, is the fact that tuples, you say they're immutable, you cannot change size, but if things are actually like lists inside are changeable, and this will be kind of shocking, maybe slightly, that you can actually adjust this, right? It's a list, you cannot change it's a list, right? I cannot change this one, right? Well, this stays, right? I cannot do Voldemars, right? This will give me an error. However, what I can do, I can mutate the list inside a tuple. Right. This is not allowed. I cannot make a new list. This is type error. However, what I can do, and this is strange, might seem strange, since my tuple, this list, is basically, as far as tuple is concerned, this is same list. It just has, again, just because it's mutable inside, tuple itself is okay. You do whatever you want inside with your in-place methods. So you can apply in-place methods to items inside tuples. Why? Because tuple is just storing sort of reference to it, right? So that's a little technical. Don't have to worry. I can even make an empty list because it's still the same empty list here, right? So now that matches, same thing. Checking for matches, same as the list. Yeah. So again, I mentioned homogeneous heterogeneous, right? Strictly, it's not a strong suggestion, but advice. So we went through or major data structure in Python today, a list which is for storing similar items, as many as you want. If you're getting into millions, then you'll have to start thinking of something else. It's not the best structure for large data storage in memory, but still good. Tuples, again, if you have something different, you can put them also together. Again, so difference the tuples only have a couple methods, count and index, right? Does not have any of the in-place methods because you can't adjust tuple size. So again, reminder, right? The lists are, we go here, right? So ordered, mutable, dynamic size, comma separated buckets, duplicates can be nested, same syntax for slicing, indexing a string. So see you guys in the next lecture. We'll talk also about functions. We have dictionaries coming up, some other structures. And best of luck.